Dan Olds here, and we are on tour stop number 7 of the 2022 Great American Supercomputing Road Trip. I am here, believe it or not, at NASA Ames, which is an amazing facility, and I'm talking to the head of the Supercomputing Division, Piyush. Introduce yourself.
Hi, my name is Piyush Mehrotra. I am the chief of the NASA Advanced Supercomputing Division here at NASA Ames in the Silicon Valley. This is a division which hosts the premier supercomputer for all of NASA, with about 1,600 users, about 600 projects. Our charter is to support all NASA missions and all NASA projects who might need large-scale simulation.
Which is quite a few of them.
Yes.
I mean, the preponderance of them, I would think, need some sort of large-scale simulation. And we actually were looking at a large-scale simulation behind us. And what is this that you have over your shoulder?
This is work being done by the ECHO Consortium, started out of MIT and JPL with associated members. They are trying to keep the global state of the ocean. They're simulating the global state of the ocean. They start off with some observational data, but then they use physics models to actually calculate the velocity, the temperature, and the salinity of water. What we are visualizing here is the velocity of the water. The lighter the color, the faster the water is moving. It allows the scientists to actually look at the gross movement and also at the fine grain movement. The grid is about 148 degrees, so about 250 million points cover the whole of Earth, and they go down 90 levels of grids.
90 levels?
Down to 5 kilometers deep.
Wow.
And the data they've collected is one of the largest sets of data, simulate data, about 5 petabytes and growing. And it's used for all kinds of research such as climate change, ice melting, debris tracking by other scientists as provided by the consortium.
And you said it's running on about 80,000 cores.
One of the largest cores it was run on was 80,000. They keep adding. They start running. For example, this particular simulation runs from about August 2012 to January 2013. But then they keep adding data to it by running it further on. And they use observational data to do midpoint corrections and things like that. And actually, currently, they're working with atmospheric model and trying to couple it so that they can get better results, both the effect of the atmosphere in it also.
Wow, that's impressive. Talk a little bit more about the computing resources you have here.
So we have 4 different systems. Pleiades, which is in the building that we're sitting in. Upstairs is one of our older systems. It's about 7 petaflops at peak.
What was that based on? I forget.
So that's all. It started off as a SGI system and is now an HPE system.
Okay.
It's an Intel-based system with multiple generations of Xeons on it.
Okay.
Because we
you sort of upgraded it in place.
We upgraded by adding more stuff as our budget allows, rather than so the whole idea is to look at how cost effective it is to run some of the older machines, and as long as we can run it profitably, then we keep it. But if we find that getting new hardware will give us more power in the same cost, then we replace the old hardware. So we keep adding until we get to the point that we replace. So that was our first machine, or actually the machine that started off in 2008. And then in about 2016, we started looking for how to expand, because we're running out of floor space, and in particular cooling and power headroom. So we did a third-party informal study, and they suggested that a modular approach would be the best for us. So we started a pilot project where we used modules to house our systems. And
now, what do you mean by modules?
They look like containers.
Oh, the containers, okay.
They look like containers,
Yep.
And we call it modular supercomputing. The biggest advantage of that was that we could make it very eco-friendly. By using the outside air at low temperatures and low humidity here in Northern California and the Bay Area to cool air cool the systems by just flowing the outside air through.
So they're air cooled, not liquid cooled.
The first one was air cooled.
Okay.
So just to give you a sense, here in the building we have 450-ton chillers with a cooling tower, and to keep the whole floor cool and take away the heat. The tower runs about 5 million gallons of water every day, and with just a 1% evaporation, we lose 50,000 gallons of water a day. So these modular systems we could run on very little water, because most of the time they were air cooled, and then if it became too hot, like 85 degrees, we had a sort of an adiabatic or swamp cooler, which was basically a fiber curtain with water flowing through it.
Sure.
And that cooled the air, and that was good enough. So we reduced the water usage by about 95% from an equivalent building-based system. And the overhead electricity was also, because we were not running those fans and things like that, it was reduced by about 90%.
Wow.
Our PUE, which is the power usage effectiveness, which is the ratio of total power to the center divided with the power to the compute, which in a typical data center around the country is 1.6. We are pretty efficient in this building at 1.33. Those things came in at 1.04, 1. Right.
You're getting near NREL numbers there.
Right.
1.04. That's
Okay.
a very good number.
And so this is one advantage. The second advantage of the modular system is the fact that we could change technology. So in the second module that we put up in the prototype, we started using water-cooled systems. So there's a closed water loop that runs, and similar technology to cool that water, but that allows us to double the capacity of the module in terms of compute resources.
But you're just cooling it with natural air. I mean,
The water loop,
you go through a chiller?
There's no chiller.
So natural air.
So the cooling technology is still the same, except instead of using air to cool the system, you're using a water loop to cool the chips on the system, and that warm water goes up to the top in this particular prototype and gets cooled by natural air. And if it gets too hot, then again you have an adiabatic cooler.
Okay, that makes sense.
That was the second advantage, that we could change the technology. And then we got permission from headquarters, because of the success of this, to actually build a whole 1 acre pad, cement pad. And so we've already put one module on there, and we filled it up. This started in 2019, so it took us 3 years to fill that up because of budget constraints, and now we're planning to put another one. Several advantages. Capital investment on the installation is just in time. Technology is just in time, and then they are eco-friendly by reducing the overall power usage and the overall water usage. So the prototype is another system called Electra, which is about 6+ petaflops. And then our Aitken system, which is the latest system, is about, if I remember, 13+ petaflops. And that we started off with Intel-based systems, and then we did some benchmarking, and now we have the about 2/3 of the racks in there have AMD Rome based. None of these systems have GPUs, because we are still sort of trying to figure out what NASA codes will utilize GPUs in a cost-effective manner. So we have coupled that to run very well, CFD codes, but that's a push that we are still doing as to
Still
look
evaluating.
We're still evaluating, still trying to port and things like that. So our GPU systems are fairly small and independent. It's a new system called Cabus, which actually is, we've just ordered some more nodes to it, so they'll come in by end of December. So those are the 4 major systems. We have some smaller systems, shared memory system. SGI had this shared memory system, so we have 2 of them, 2 terabyte shared memory systems, and a smaller system.
The big scale ups.
Yeah.
Nice.
Yeah.
Nice. And you know, it's funny, that SMP model, shared memory model, I still have the belief that pretty much any application will run faster on shared memory than on distributed memory. Am I wrong?
Well, I mean, in shared memory, you can do even message passing on top of it.
Yeah, but
So-
through the memory, so it's much, much quicker.
It's much, much quicker than going through across the
Across
InfiniBand.
a physical-
InfiniBand.
Yeah.
But the whole approach, programming approach, is different. You
That's
have to
true.
use OpenMP. You have to. I mean, in fact, most of the codes that we now have are exploiting OpenMP underneath the MPI
Yeah.
within a single
So you
node.
have to pull that out.
Right.
Yeah.
Because there's so many cores in there. So
Yeah.
the newer chips have so many cores that you might as well try and use shared memory where you can and get multi-level of parallelism.
Let me change this up a little bit. Are you using public clouds at all?
So not directly. NASA is, to a large extent. There are a lot of enterprise effort that has gone into the public cloud, and a lot of the science people who are going are putting their projects on the cloud. In fact, there is a big push from the Science Mission Directorate for open science, open data, because the charter of NASA is to provide the data to the public. So there's a big effort called TOPS towards open platforms, which is putting a lot of the observational data on the cloud. Okay.
Okay.
So that push is there. Now, we started here several years ago, actually. I did a first study back in 2012, and then we repeated in 2018, comparing the sort of performance of cloud to our on-prem systems. And in those days, we found that the cloud performance sometimes was a factor of 2 or 3 less than what we had on-prem. Now, recently, when we've done some benchmarking, that is not true. Performance of clouds is approximately equal, plus minus, sometimes in fact a little faster, sometimes slower, but within reasonable bounds. The problem we found is that the compute cost of the cloud is significantly higher by at least 2 to 3 factors. And in fact, when we compare it, we compare our overall cost, including labor and user help and networking and storage, to just the compute costs. So what we found that is, for large-scale simulation, HPC kind of work, it is still more cost-effective to be on-prem.
Yeah.
But there are several advantages to the cloud. You can get access to newer technology faster.
Yeah.
We are a government bureaucracy, so it takes time for us to bring it in. So if you want to test anything at scale, for example, maybe 18 months ago, or a year ago, when we didn't have access to A100s, we used the cloud.
Yeah.
It
to
also-
test and to see if it was going to be a good
Fit for
perfect.
us.
That's a great use for the cloud.
And then the other good use is when we have people who need systems immediately.
An emergency.
Well,
kind of
a
like
sense.
an emergency, but-
Yeah, but I mean, the point is our systems are utilized about 80–90% of the time.
Yeah.
So our queues can become fairly long. And if you have milestones that you have to meet and things like that, and you're not, you can be given priority. We do give priority to a lot of folks, but if they need, then they can go on the cloud and grab resources on demand.
That makes sense.
So those are the use cases that we have. Now, let me go back and say something else
Yeah.
about the cloud. Like I said, there's a push to do open science. What means is that a lot of the workflow is being done on the analysis of the data on the cloud. What these projects have found is that the clouds provide great services for data management and things like that, but when they're starting to do large-scale analysis, the costs are ballooning up. So what we're looking at is a hybrid infrastructure. This is something that we started about a year ago, 6 months ago, that we started working on this, where the vision is that if you have a workflow, you have the data on the cloud, you're working the components on the cloud. But if you have a component which is much more compute intensive, you try and bring it up on-prem. So you do the components which are appropriate for the appropriate hardware Okay. Obviously, there are lots of issues with that as to how you bring the code over using containers. Biggest issue is data management because the data is on the cloud. You've got to pay the egress cost of bringing it in here. And then do you duplicate it here? Do you keep cache it? Or how do you manage that whole dual system, syncing the file storage and things like that? And one bigger thing is that these workflows are joined with sort of third parties, like NASA is working with the European Space Agency, or they're working with universities who may not have credentials, NASA credentials, to be able to run here. So how do we manage the security issues of non-NASA personnel being able to launch jobs here is a critical issue that we have, because according to the federal government and NASA, you cannot just run jobs, give access willy-nilly to anybody and everybody. No. So those are the kinds of things. How do you do code management, research management, data management, security management? These are the sort of
it's a lot of
things,
issues.
Lots of issues, but we are pushing towards it. We hope we have some prototype projects that are actually running, and we'll be trying to put together the whole infrastructure so all the data analysis frameworks should be able to run.
Okay, well, looking a little deeper into architectures and coming architectures, there are some new changes that we're seeing with being able to compose systems that's coming down the road with some other designs like Cerebrus, massive scale, wafer scale computing. Are you guys looking into any of that?
We try and keep up with the technology. Obviously, our budget and resources are limited and not as some of the other agencies' budget. So keeping our systems up is a big issue. But doing the best science and engineering is also, that is the major charter for this facility. So we keep track of those technologies and try and bring it in. We've got a NEC vector engine that we are working with, benchmarking it. So whenever we get a chance, we do benchmark this to see if it is useful for NASA applications. And it is really up to the users to figure out whether they want some system like that. For example, AIML, we're obviously tracking it. The usage is not increased to the level that we have to bring in a huge bunch of GPUs and use them in a manner, in a heavily utilized manner. The same thing with CFD codes or all kinds of science codes. Like I said, we've got a few codes that can run effectively on the GPUs, but a lot of them don't. So we are very conscious of how much utilization there is, and then we spend the budget on bringing the right technologies in. So we go through the process of evaluating the technologies and keeping track of technologies, and then when we see that the usage is increasing, we bring those technologies in a production manner. So we're looking at everything.
But you're looking for the users to pull in what features they need to tell you.
Right, exactly.
Okay.
We'll help them.
Yeah, of course.
Okay, because the users generally are more interested in the science and not on how it's running.
Yes.
So we have a group of application engineers who will work with the users to see if their code could utilize those features. And once we have that, then we can say, okay, now you've got a code that runs on this technology, would you use it for production runs? And as those production runs increase, then we can bring in a larger scale technology in.
That makes sense.
Yeah.
And I would imagine that the answer is probably about the same for quantum computing.
So quantum computing, actually, till recently, we had a quantum computer, D-Wave. Well, similar to annealing computer.
The D-Wave.
The D-Wave, right?
Yeah.
Behind me in that basement there.
Ah, okay.
Till about a year ago.
I thought I felt a little chilly, but it's not here anymore. Okay.
Not here anymore. So we did have it. It was a joint project with Google and USRA and us, where Google leased the machine and we led the research on it. So that's gone, but there's a big group in one of my sister divisions, which is actually looking at quantum computing. They are working with different kinds of hardware vendors to evaluate their systems from the quantum algorithms point of view. Also looking at different quantum algorithms for different aspects where NASA is interested in. Scheduling is the one big huge thing. And I think the third leg for the group is just looking at how to use these machines, the compilers and things like that.
Yeah.
So they're working with both the hardware, the software, and the algorithms. It's a significant group about
that. I mean, the way it looks now, it's like quantum is going to be like a super accelerator.
That's what I've always said, that I don't see it working on its own end-to-end workflow kind of thing, but the things that it is good at can be partitioned off and sent to that's always what my vision was.
That's what makes sense to me too.
Yeah,
I think we're going to see a lot of quantum simulators coming out in the next year or two and coming into wide use. Are you going to be using any of the exascale systems?
So we have a few projects that are leveraging that, but it is they have to go through the process of figuring out how to get the access and whether they will be granted access. One of our biggest issues is the fact that there is, for us, no midpoint kind of thing for as a stepping stone to get to that exascale DOE exascale system. Now, having said that, I am working with some DOE folks to try and see how we could manage to get some codes running on smaller systems, GPU systems, so that then we can step up to the larger system. So we're talking about collaboration with DOE and trying to see why we can, like I said, we've only got 2 or 3 codes at this point that can actually use GPUs at scale.
Yeah, and those exascale systems are heavily GPU.
Oh, absolutely. If you're not using, I think 25% of the system, I don't know exactly what
it's some huge. I mean, it's 4 per node, I believe, 4 GPUs.
No, but if the application cannot use 25% of the system, they don't want it on their system.
Makes sense.
And
yeah,
we don't.
That's a big application.
That's a big scale.
Yes.
Yes. So we're working with them and trying to see how we can get onto them. And the ECP, the Exascale Computing Project, is very interested in collaborating with us.
Well, so we just both got back from SC22. What did you see that was interesting or exciting there? Or what did you hear about?
Lots of new technologies, the push in the hardware, the push in high bandwidth memory, those kind of things. I was at a very interesting panel on edge computing in space. Because I mean, NASA is obviously interested in it. You've got a system which is running up there somewhere in Mars. It'll take several minutes for the commands to come back. So you want to do as much computing there as you want to do it
Yes,
here.
you do. You can't just send all the data back to Earth.
Exactly. So that's the other data reduction at the source or the edge. Before you send the data back. Those kind of work that's done. HPE and SGI before that had a pilot project where they put commercial nodes up on the space station.
That's right, I remember that.
Yeah, and they've actually gone through the second phase of it. Microsoft did some analysis, a project which is a very interesting project on analyzing your gloves, because after a extravehicle journey, they have to again examine the gloves, because if there are cracks or anything like that, they can't reuse it. And that takes several weeks to do it. And they looked at, what they did was, I think this is Jennifer Ott and her group at Microsoft Azure. They looked at images and used AIML to analyze that and give them the code information to the decision makers within minutes instead of within weeks, kind of thing. And that was all being done. So those are the kinds of things that you would do at the edge before you actually came back. Edge computing is going to be very important for us. We're looking at computing to be able to reduce the amount of watts used for any computing, put them on these little nano satellites for looking at the sun, or those kind of things. So that was a really interesting panel. That was
That's very interesting. Anything else?
A lot of more of the same kind of thing. That's
more evolutionary stuff.
more
as opposed to
evolutionary stuff.
revolution.
Yeah.
Okay.
Yeah. Like I was saying, HP had this rover sitting there.
I saw that. Yeah.
Yeah, I mean, obviously it's not, they're still going to propose it, but that had some computers on it also.
I'll bet. Yeah. You saw the Cray system there.
And
right?
and saw the Cray system.
Wasn't that neat?
Oh, absolutely. I hadn't realized I had never seen the Cray system.
Oh, really?
And no, the actual system, I've got a picture upstairs. Didn't realize it was so small.
It's, yeah.
Yeah. And that whole story about ladies being used who could crochet, I could see how
To get your hands in.
well, they had to put all the wires together and connect the wires, and I can see why they would use ladies who are so efficient at crocheting.
With small hands.
With small hands and getting in there.
In addition.
Yeah.
Yeah, that's incredible. And I took some cluster competition kids down there, and I said, this was built by hand. No. Oh, yeah. This is by hand. Ladies with small hands. They didn't believe me. Which was kind of funny. So, assume that you're addressing all of the HPC vendors out there. What do you need in 3 years?
What do I need in 3 years?
And I'm asking 3 because they can change course between now and then. Between now and 12 months, they don't have as much flexibility or latitude. What do you need?
Oh, wow.
What do you want?
Well, high bandwidth memory being available everywhere. That's a big issue that we have. I saw some work, particularly with accelerators, and being able to have the CPUs and the accelerators access all the memory without having to push it back and forth kind of thing. That would allow pieces of the code that need to run where they're most appropriate without paying the penalty of data transfers and things like that. Those are obviously the biggest things to get the codes up and running and getting the performance that they need. Networking also, inter-node networking is a big issue. From sort of a little bit of the software point of view, fault tolerance has been a big issue.
Really?
Yes. I mean, if you have an MPI code and one node goes down or multiple nodes go down, how does the code recover from that? So it's not hardware in that sense, but it is certainly software. So some of these are some of the things that would be interesting to see in the next 3 years. And I think they're already making a push for them. They're already getting towards this. So maybe it's not 3 years, maybe a year, or which may be available in new systems. So.
And so, finally, wrapping up, what excites you about supercomputing right now?
I mean, what excites me is the kind of things that we can do.
Doing this stuff.
Doing this stuff. Being able to help the users, being able to... Artemis just launched just a few days ago. Here, in the division itself, there's several projects which have been which have supported Artemis. We have been doing what is called aero databases, so various designs. These are small runs, 1,000 cores, 4,000 cores, but thousands of them to analyze the different configurations. So you fill a database worth of parameter study kind of runs, so that the decision makers have a way of figuring out what designs are good and things like that. Then we've, I can show the simulation, we've done an analysis of the launch environment. Because these SLS rockets are much larger, so they came to us and said, what about, can we design an environment, we're designing an environment, can you analyze and tell us what the pressures would be, what the temperatures would be, how's the acoustic characteristics of that, okay? So the whole analysis of the launch environment. Another project that was done here, booster separation. When the boosters separate, you've got to be careful that as they separate, they don't come back and bang the
No.
vehicle and things like that.
No, that's
So-
a key point.
Yeah, so that whole analysis has been done here using CFD. One more project was launch abort vehicle. So NASA is always concerned with the astronaut safety, and so they have a launch abort system which, if something goes wrong with the rocket, it will just at very high speed separate from the rest of them, just take the astronauts away. Well, the multiple G effects on it, but you don't want it vibrating so hard that the health
That
of
harms the pilots.
that harms the pilot. So that kind of, all of this has been done using CFD analysis on our systems. So this is something that we do. We help NASA push its missions, not only in the exploration part, in aeronautics research, green aviation, looking at the Earth, exoplanet search. So there are a lot of projects which are supporting NASA missions across the board. And that's what is exciting, that we can actually provide the resources for the scientists to get their work done and produce it, and which gets not just for science and pure research, but to explore in the world.
Right now, we're orbiting the moon.
Right, exactly.
First time back in 50 years.
Absolutely.
And that's a great thing. And you guys make that happen.
We are here to serve.
Fantastic. Well, thank you so much for your time. I really appreciate it.
Thank you.
And we will talk to you again soon.
Thank you.
500 miles of open